Hello everyone, this is Professor Roman. Let's continue the group theory lectures. We're ready now to look at chapter 3 of the book, and in this chapter we're going to discuss two of the most important families of groups, the symmetric groups and the free groups. We'll take a reasonably close look at the symmetric groups in this chapter, but postpone a more detailed look for a later chapter. And also, I'm going to postpone some of the proofs till that later chapter, but I encourage you now to try to supply the proofs yourself. As far as free groups are concerned, we'll do what we need to do in this chapter on free groups, so we won't have to revisit them later, except in examples or exercises. As I said, the symmetric groups form a family of groups. For each non-empty set X, there is one symmetric group, and it is denoted generally by S sub X. The symmetric groups are, without doubt, the single most important family of groups. And the reason for this is that the symmetric groups contain isomorphic copies of every group, finite or infinite. So put more formally, for any group G, there's an embedding sigma from G to this symmetric group. This is S sub G. So here, this G is, we're really thinking of it just as a set, the underlying set. So the image, sigma of G, is an exact copy, an isomorphic copy of G that lies within that symmetric group. This is the content of a very famous theorem of group theory called Cayley's theorem, and we will prove that in this chapter. It's surprisingly easy, actually. If X is a non-empty set, then a bijective function from X to itself is also called a permutation of X. Actually, the term permutation is more commonly used for finite sets X, but it still applies to infinite sets. And there are various notations for permutations, especially in the finite case. So if X is this finite set A1 through AN, then this notation, it's a two-row matrix, is used to denote the permutation that sends an element in the top row to the corresponding element below it. So AJ goes to BJ for all j between 1 and n. So just as an example, this permutation sends 1 to 3, 2 to 1, 3 to 2, and 4 to 4. And sometimes I will write that in this notation, which I think is clear, easy to read. 1 goes to 3, which goes to 2, which goes to 1, 4 goes to itself. Now the set S sub X of all permutations on X is a group under composition. Composition of functions is associative. The identity function on X is a permutation, it's a bijection, and it acts as the identity under composition, as we all know. And every permutation has an inverse permutation under composition. So we have a group, composition becomes the group product, and composition is generally just referred to as the product. Here's the formal definition. If X is a non-empty set, then the set S sub X of all permutations of X is a group under composition called the symmetric group on the set X. we'll denote the identity permutation by the Greek letter iota. Any subgroup of a symmetric group is called a permutation group. In this book, in this course, we'll be concerned primarily with symmetric groups on finite sets. But regardless, it's fairly clear that if x and y are sets, let's say finite sets of the same size n, or even infinite sets of the same cardinality, then from a group theoretic point of view, there's very little difference between the two symmetric groups S sub x and S sub y. In fact, it's just a relabeling of the elements to which the permutations apply, a relabeling of the domains. And more formally, if we have two sets of the same cardinality, then the symmetric groups are, in fact, isomorphic. And I'll let you prove that. So, as is customary for finite sets x, we, instead of using an arbitrary finite set x, we will use this set. Oops, sorry about that. I sub n. And denote the symmetric group on this set, rather than writing S sub I sub n, we'll just write S sub n. So Sn is the symmetric group on these symbols, 1 through n. And anything we prove of a group theoretic nature for Sn applies to any S sub x if x has size n, because of the isomorphism. Sn, as you probably know, has size n factorial because there are n factorial permutations of size n. So the permutation, the symmetric groups get rather large quickly. For n equals 20, this is the order of the symmetric group, obviously. And so these do get very large, and that's what you would expect in view of Cayley's theorem from a family of groups that contains, in a sense, all groups. It's got to be pretty large. Here's some terminology that will be very important to us. If sigma and tau are permutations in Sx, then sigma fixes an element little x of x if sigma of little x equals little x. And it moves little x if sigma of x is not equal to x. The support of sigma is the set of elements that are moved, and this is the notation we'll use. The fixed set of sigma is the set of elements in capital X that are fixed. The permutations sigma and tau are disjoint if their supports are disjoint. Another way to say that is that if an element little x in capital X is moved by one of the permutations, it must be fixed by the other. In other words, no element is moved by both permutations. As to commutativity of the symmetric groups, if the size of the set X is at least 3, then the symmetric group is non-abelian. And that shouldn't be a big surprise either, because if, in view, again, of Cayley's theorem, if the symmetric groups are going to contain all groups, they're going to contain the all non-abelian groups. So at least some of the symmetric groups have to be non-abelian. An abelian group cannot contain an isomorphic copy of a non-abelian group. Okay. So to see this, we I'm going to use this notation, which we'll introduce formally in a little while. This is looks like an ordered pair, but with a space rather than a comma. This denotes the permutation of capital X that interchanges the two elements x and y and leaves all the other elements of x fixed. This is called a transposition, as we'll introduce formally in a little while. So this is what the transposition does. It sends x to y, y to x, and every z goes to itself if it's different from x and y. Well, for distinct x, y, and z in capital X, it's easy to see that these two transpositions do not commute. If you look at this side, x goes to z, but is fixed by this, so it comes out z. So x is sent to z on this side. X is sent to y here, which is fixed by this transposition, so x goes to y on this side. So these two permutations do something different to x, and therefore not equal. On the other hand, it is the case that disjoint permutations commute, and this is critically important for the study of permutations. After all, any little x in capital X is moved by at most one of the two permutations because they're disjoint. And so it's basically ignored by the other one. It is ignored, it's fixed by the other one, or by both if neither one moves x. So it's pretty clear that when you apply both permutations to x, it's the same as just applying the one that actually moves x. Anyway, I'm going to leave a formal proof of that to you. It's good practice. Disjoint permutations in S sub x commute. X doesn't have to be finite here, it doesn't matter. There are special types of permutations that we need to look at because they form the building blocks of all permutations. Transpositions are one such type. If A1 through AK are distinct elements of the set X, then this expression, and I've used dots here, oftentimes it'll just be spaces if the elements are actually written out. For example, 1, 2, 3, it'll look like that. Sometimes we have to put commas if we need to do so for readability's sake. That'll happen once or twice. But this notation denotes a permutation, which I'll call sigma, that sends each element in this list to the next one to the right, but wraps around. So AK goes to A1. So AI is sent to AI plus 1 for all I between 1 and K minus 1, but for I equals K, AK is sent to A1. Also, all the other elements of capital X, if there are any, are fixed. So just as an illustration, I should say, this type of permutation, because there are K elements, is called a K cycle. So as an example, in S6, this is a 4 cycle. This is a 4 cycle in S4, in S5, in S6, and any larger permutation, symmetric group. This cycle sends 1 to 5, and then to 4, and then to 2, then back to 1. And since we're in S6, and 3 and 6 are not included here, they're fixed. This set, the set of elements that are in fact moved, is called the underlying set for the k-cycle. Actually, when k equals 1, there's a little issue. I should not have said that the element is moved, because if this was just a singleton set, it wouldn't be moved. But in any case, as long as k is bigger than or equal to 2, the underlying set is the same as the support, the things that are moved. Each a sub I we'll call an element of the cycle. And we'll also say that a k-cycle has length k. So a cycle of length k is another way to say k-cycle. And I will leave it to you to show that a k-cycle has order k. If you raise a k-cycle to the power k, you get the identity. But if you raise to any smaller power, you do not get the identity. So the order of a cycle is equal to its length. A one cycle is simply the identity permutation, because if you want to say it this way, A gets wrapped around to itself. But everything else that's not A is fixed as well. So this one cycle fixes everything. It's the identity. Two cycles, as we discussed briefly, are called transpositions because they interchange the two elements A and B. They leave everything else fixed. Transpositions are involutions. They have order 2. They have length 2 and order 2. There are other permutations that are involutions that have order 2 besides the transpositions. Also, it's important to note that a k-cycle can be written in k different ways. Here's a 4 cycle, 1, 2, 3, 4. This is the same cycle. I just rotated the elements but didn't change their order, their relative order. So 2 goes to 3, 3 goes to 4, 4 goes to 1, 1 goes to 2, just like this. All 4 of these are exactly the same function. Now, I've had some students come to me in the past a little confused about another matter. If they've taken discrete math or combinatorics or a transition course, they're familiar with ordered arrangements, which are also called permutations of elements A1 through AK. So, for example, these are 2 ordered arrangements of the numbers 1, 2, 3, 4. They are permutations of 1, 2, 3, 4. They're not viewed essentially as functions. They're viewed as just reordering of the numbers 1, 2, 3, 4. If you want to view them technically as functions, which they are, as bijections, they are these 2 bijections. So 2, 3, 4, 1 goes down in the second row here. The top row is 1, 2, 3, 4. Same thing for this one. Well, these are distinct. They're not the same they're not the same bijection. They're not the same ordered arrangement. But these 2 cycles are the same. So you have to be careful not to confuse this notation, which represents a cycle, a particular type of permutation, with this notation, which is an ordered arrangement, which is also a permutation. But these 2, while they look quite similar, the parentheses make a world of difference. They are defined, they are bijections defined differently. So I hope that helps avoid some confusion there, in case you had any. In the symmetric group, composition is generally denoted by juxtaposition. So just to illustrate, I probably don't need to do this, but here is a product of two 3 cycles, 2 permutations. It is composition, and you know how to do composition. So for example, if you want to apply sigma to the number 4, you would start with the right-hand function. 4 is sent to 5. 5 is left alone by the left-hand function, so sigma of 4 is equal to 5. Sigma of 3, on the other hand, 3 is first sent to 4 by the right-hand function. 4 is then sent to 2 by the left-hand function, so sigma of 3 is equal to 2. One other thing I should mention is that if sigma is a cycle, its powers need not be a cycle. And I would invite you to provide a simple example. Sometimes some powers of a cycle may be a cycle. Some other powers may not be a cycle. It may be a product of cycles. So that's something for you to experiment with. One of the strongest tools in the study of finite symmetric groups, S sub n, is factorization. And in general, there are 2 useful ways to factor permutation in Sn, either as a product of cycles or a product of transpositions. It's a fundamental fact that every permutation, sigma in Sn, is a product of pairwise disjoint cycles. And this product is in fact unique, except, of course, for the order of the factors. Since the factors are disjoint, they commute, and so you can't control the order. That's not unique. This factorization is called the cycle decomposition of sigma. And the word "the" is a little misleading. "The" tends to mean unique. It's only unique up to the order of the factors, but everyone says the cycle decomposition. I suppose some say a cycle decomposition. That's a little more accurate, but could be misconstrued as meaning there are fundamentally different cycle decompositions when there are not. Only the order is non-unique. Now I'm going to prove this in a later chapter, but what I want to do now is look at an example of the cycle decomposition, and I think you'll see from the example how easy it will be to generalize this to arbitrary permutations. So consider this permutation in S6. To find its cycle decomposition, we could start with any number in the top row, but we'll start with 1 and follow 1 as we apply sigma as many times as necessary to return to 1. 1 goes to 6, 6 goes to 1, so that didn't take long, and we have 1, 6, 1, and that is the transposition 1, 6. Now, one thing that needs to be clarified is that if you start with any particular integer, say 1, and continue to apply sigma, you will indeed eventually get back to 1. And I'll let you ponder that. So we have our transposition here, 1, 6. Then we do the same thing for the next unused integer 2. 2 will go to 5, and 5 will go to 3, and 3 will go to 2. So 2 to 5 to 3 to 2, that is a 3 cycle. We're still missing 4, but 4 goes to itself, and so that produces a 1 cycle. Then we take the composition, or product, of these 3 cycles in any order. Doesn't matter because they commute. They are pairwise disjoint. And that is also something that needs to be verified, that always happens. And so we get this product, and that is equal to sigma. It sends 1 to 6, 2 to 5, then to 3, then to 2, and 4 is fixed. This is the cycle decomposition of sigma. And as I mentioned before, it's not terribly difficult to show that this process always works to produce a product of pairwise disjoint cycles that's equal to the original permutation. Notice that we can drop the 1 cycle, and so sigma is in fact this product. The 1 cycle is the identity. However, by definition, the cycle decomposition includes the 1 cycles. If they're missing, you can, of course, restore them. You know what they must be, but technically speaking, the 1 cycles are part of the cycle decomposition. Now let's talk about the order of an arbitrary permutation. We've already mentioned, I left for you to prove, that the order of a k-cycle is equal to its length, k. Well, the cycle decomposition is going to be a big help in determining the order of an arbitrary permutation. So the place to start is to decompose our permutation sigma into a product of disjoint cycles. Because these cycles are disjoint, they commute. If we raise sigma to the kth power, it will look like this. And we can raise each cycle, each factor, to the kth power. Now, I mentioned already that these powers are not necessarily cycles, but they are permutations, so they will be a product of cycles. And these powers of cycles are pairwise disjoint. I forgot the word pairwise here. So, sigma to the k will equal the identity if and only if each of these factors is equal to the identity, because the factors are pairwise disjoint. And that holds if and only if the order of each cycle divides k. This is saying that k is an exponent for that cycle. And that's equivalent, because we know the order of a cycle is equal to its length, that the length of each cycle divides k. Or in other words, k is a common multiple of the cycle lengths. Well then, the smallest positive such exponent k will be the least common multiple of the cycle lengths. So to compute the order of a permutation, it is simply the least common multiple of the lengths of the cycles in the cycle decomposition. That is quite simple then. It's not always easy to determine the order of an element in an arbitrary group, but for these groups it's relatively simple. This could easily be programmed into a computer. The cycle structure, also called the cycle type of a permutation, is just a list of the number of cycles of each length. Not the cycles themselves, just the number of cycles of each length. So let's look at this permutation. Notice, by the way, that I made the spaces much larger because I have a 10 and an 11 two-digit numbers, and so if if this space wasn't really exaggerated, you might mistake this for the cycle of length 1 containing 910, or you might misconstrue this to be the transposition that interchanges one with itself. Of course, that's not a transposition, but there's potential for misunderstanding here, so I could have used commas, but I decided just to make the spaces bigger. The cycle structure of sigma consists of 2 cycles of length 3, 2 cycles of length 2, and 1 cycle of length 1. This notation is often used to represent cycle structure. 2 cycles of length 3, 2 cycles of length 2, 1 cycle of length 1. Sometimes dot patterns are used to denote the cycle structure. Questions about cycle structures often find their way onto exams. They make relatively easy questions. I've even seen them on comprehensive exams for students wanting to move on to a PhD program. Any K-cycle in SN can be written as a product of transpositions. You have to use one of these two formulas. For a 1 cycle, you just write it this way. This product is the identity, and so that's equal to this 1 cycle. If K is bigger than or equal to 2, then you have this formula. Excuse me for a moment. Then you have a formula here. This K cycle, A1 through AK, is equal to this product of transpositions. It may look a little difficult to remember, but it's not that bad, because the first element of the cycle appears as the first element of each transposition. The other elements appear in reverse order, or in descending order if you prefer to go from left to right. Okay, so that may help you remember this. Here's an example. This 4 cycle would be 1, 6, 1, 3, 1, 5. 1, 6, 1, 3, 1, 5. And here is the 1 cycle. Because of these formulas, any permutation is a product of transpositions. All we have to do is first form the cycle decomposition and then write each cycle as a product of transpositions. This gives us our second important factorization, which we'll call the transposition decomposition of a permutation. Now you might be thinking, and it might seem at first, that factorization into transpositions, which are relatively simple permutations, would be much better than the cycle decomposition. But unlike the cycle decomposition, the transpositions are generally not disjoint. You can see that right here from this formula. These transpositions are not disjoint. They do not commute. So the factorization into transpositions becomes more complicated, more complex, because the factors don't commute. That makes it harder to work with in many respects. The truth really is that both decompositions have their uses. It depends on the circumstances. Another problem with the transposition factorization is that it's by no means unique, even up to the order of the transpositions. A single transposition can also be written as a product of 3 other transpositions, so there's no uniqueness in this sense. But there is one remarkable fact about transposition decompositions in terms of uniqueness. The parity of the number of transpositions is always the same, no matter how you decompose into a product of transpositions. If one such decomposition is into an even number of transpositions, all such decompositions must have an even number of transpositions. And the same statement for odd. So that's quite remarkable. And there are many proofs of this relatively famous theorem, and I'll provide one for you in a later chapter. So it's something you might want to ponder now for your own practice. So a permutation that can be factored into a product of an even number of transpositions is called an even permutation. That definition is well defined because of what we just said. If one decomposition has an even number of factors, they all do. Similarly, a permutation is odd if it can be written as a product of an odd number of transpositions. If we look again at these formulas, you'll notice something. This is a cycle of length k. There are k minus 1 factors here. So if k is even, there are an odd number of factors. If k is odd, there are an even number of factors. Also here, this is a one cycle, one is odd. There are 2 factors, an even number of factors. So, in summary then, we've already seen, or I've asked you to show, that the length of a cycle is equal to its order, but also an odd length cycle is actually an even permutation, because there's one less factor here than the length, or order if you want, of this cycle. And an even length cycle is an odd permutation. That's just the way it turned out, so I have to live with it. Let's look at the center of the symmetric groups Sn. You would expect, at least for n not trivially small, that the symmetric group, being rather large and being rather complex, it would be difficult for a single permutation to commute with all other permutations. A single non-identity permutation, of course. And that's the case. When n is bigger than or equal to 3, Sn has trivial center. It is centerless. And I'm leaving that as an exercise. Shouldn't be too bad. All you have to do is produce 2 permutations that don't commute. And you can do that with cycles. And I shouldn't be giving that away. But